So we just learned how to calculate different measures of concentration. Now we're going to use those information to help us understand something called the colligative properties of solution. So it turns out that when you mix a solvent with a solute, there are certain properties that appear in the solution that change compared to how those properties look like in the solvent. And so these are what we call colligative properties when the properties depend only on the concentration of the solute molecules but not on the identity of the solute. So in other words, let's say I'm dissolving potassium chloride into water, and then in another solution, I'm dissolving sodium bromide into water as well. And if the concentration of those two solutes happen to be identical, we're going to observe the same property appearing in both solutions, despite the fact that the two solutions have different types of solutes. So we're going to look at each of those properties, which are listed here. So the first one is called vapor pressure lowering, and then boiling point elevation, freezing point depression, and osmotic pressure. Now, because these properties depend on solute particles, one of the things that we have to differentiate early on is the type of solutes that we have, whether it's an electrolyte or a non-electrolyte. The reason this is important is because electrolyte will dissociate to form more particles than the number that it is dissolved in. So for example, for a strong electrolyte, if you have 1 mole of solute that you dissolve in water, you're going to generate a lot more than 1 mole of solute particle. We know this from our discussion of strong electrolytes, which are soluble salts, strong acids, or strong bases in General Chemistry 1. With weak electrolytes, we know they're going to partially dissociate to produce additional number of ions. It's just not going to be as many as the strong electrolyte. So in this case, if you have 1 mole dissolved, you're still going to produce more than 1 mole. It's just not going to be as much as the strong electrolyte. And then the non-electrolyte, where you dissolve 1 mole, you're also going to generate 1 mole of the solute that's dissolved in solution. So there has to be a little bit of differentiation between the electrolytes and the non-electrolytes. We're going to talk a lot more about this at the end of this chapter, about how we quantify the number of ions that are produced in the electrolyte. But right now we're going to focus primarily on the colligative property of non-electrolyte. So the first colligative property is what we refer to as vapor pressure lowering. And in order for us to understand that, we have to first understand what vapor pressure is. This is a concept discussed in General Chemistry 1, but I want to bring it back up here to have you remember what it is. And the idea of vapor pressure is just that if you have a container of liquid that is closed, the particles of the liquid that are on the surface is going to be able to escape some of the intermolecular forces that exist in the liquid, and it will form the gas particle, okay, of the same substance. Right? And if you leave this to happen over time, eventually some of that gas particles would go back to become liquid, some of the liquid is going to evaporate to become gas, and you reach what we call a physical equilibrium, where the rate of the liquid becoming gas is the same as the rate of the gas becoming liquid. At that point, when the system reaches equilibrium, you can measure the pressure that exists here on the top of the liquid, and that's what we refer to as vapor pressure of the liquid. And so every liquid will have a certain amount of vapor pressure, and liquids that have higher vapor pressure at a given temperature is what we call volatile liquid, whereas a liquid that has very low or no vapor pressure at a certain temperature is what we call non-volatile liquid. One of the interesting things discovered about solutions early on is by French scientist Francois Raoult, and he found that in solution, when you add solute to a solvent, we see that the vapor pressure of the solution actually is lower than the vapor pressure of the pure solvent. So here's a picture that shows that phenomenon. Here's the solvent, which is just pure water here. And as I said earlier, some amount of that liquid is going to escape to form gas. And at equilibrium, we can measure that vapor pressure. So it's given here at the top. And when you add some solute in there, let's say sugar or salt or something else, you notice that that vapor pressure value now is lower than what it was before. The explanation for this is actually not too difficult. There's sort of a couple of ways to explain this, but I'm going to use the simpler explanation, which is that when you add some of that solute into the solvent, this is what happens. So initially, all the molecules on the surface of the liquid is able to escape and become the gas particles that generates that vapor pressure. When you put the solute here, and we're just going to first focus on non-volatile solute, some of that solute will take up space on the surface of that liquid, right? And so as a result, there are fewer solvent particles that could occupy that space. Because there's fewer solvent particles that occupies that space, there's also fewer of those solvent particles that could escape into the gas phase, thereby resulting in a lower vapor pressure of ocean compared to the vapor pressure of the pure solvent. And so that's the phenomenon that we're going to look at here. Now, Raoult's discovery was specifically for what we refer to as
ideal solution.
Now, this is a concept that I discussed in an earlier section on this chapter, and I had differentiated between what I call an ideal solution versus a non-ideal solution. So this picture here should explain again what the difference between those two types of solutions are. An ideal solution is a solution where when you mix the
solvent and solute,
the type of intermolecular interactions that happen solvent and solute in the mixture, okay, is the same as the type of interaction you observe in the solvent-solvent and in the solute-solute. So in other words, if you recall this equation here, delta H of solution is equal to delta H of solute plus delta H of solvent plus delta H of mix. An ideal solution is one where the absolute value of the delta H of mix is the same as the absolute value of the sum of the delta H of solute versus delta H of solvent. So in other words, you can think of the mixture as pretty much the same in terms of the strength of interaction as what exists before the two things are mixed together. And we have talked about what some examples of these type of solutions are. If you have two nonpolar solutions that are very similar in terms of the types of molecule, then we're going to get an ideal solution. Non-ideal solution would be one where the interactions between solute-solvent is not the same strength as the one in ideal solution. So this picture here shows what a non-ideal solution could be. So here, for example, the interactions between blue particles are stronger compared to the interactions between the blue and the red. So the blue and the red seems to be avoiding each other. They're a little bit further apart compared to the blue and the, okay? And so that's telling you that there's some non-ideality, whereas in the picture here for the ideal solution, the blue and the red has pretty much the same distance as the blue and the blue and the red and the red. Okay, we're going to talk a little bit later about how the observation changed a little bit when we're talking about non-ideal solution, but right now we're just talking about ideal solution. So again, Raoult's observation was made originally on ideal solution, which typically just means something that's fairly dilute. And he discovered that the change in that vapor pressure is proportional to the mole fraction of the solvent. So in fact, he developed an equation that explains how to calculate the vapor pressure of the solution once you put in some non-volatile solute in it. And this is called Raoult's law. And it's just vapor pressure of the solution is now equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So how each of those variables is defined. And so it just means that originally in the pure solvent,
the mole fraction of the solvent is 1, so the pressure is equal to the pressure of the pure solvent only.
But then as you add some solute, the mole fraction of the solvent would drop. So let's say it's 70% now. So then the vapor pressure, which comes only from the solvent, would just be 70% of the vapor pressure of the pure solvent. Okay, so it's hopefully pretty easy to kind of understand what that equation means. I already defined what non-volatile means earlier. It's something that doesn't have vapor pressure. And then non-electrolyte, of course, we also know what the meaning of that term is. Now, the vapor pressure lowering, okay, so think about the difference between those two words, right? Vapor pressure versus vapor pressure lowering. Vapor pressure lowering just means to the actual difference between the vapor pressure of the pure solvent and the vapor pressure of the solution. So in other words, the vapor pressure lowering we can call delta P is just P naught, vapor pressure of the pure solvent, minus P, which is vapor pressure of the solution. And of course, vapor pressure of the solution, we just said earlier, is equal to mole fraction of solvent times P naught. We can factor out the P naught here, so this becomes P naught times 1 minus the mole fraction of the solvent. But 1 minus mole fraction of the solvent is just mole fraction of the solute, right? Because as you recall, if we have two components, mole fraction of A plus mole fraction of B should equal to 1. Okay, all right, so we have a couple of equations there that we can use to calculate vapor pressure of a solution. So here's a quick example to show how this works. It says calculate the vapor pressure lowering, delta P in this case, of a solution that contains 2 grams of aspirin, given the molar mass of aspirin there, and 50 grams of methanol, and you're given the formula of methanol it tells you methanol has a vapor pressure of 101 torr at this temperature, so that immediately tells you that methanol in this case is the solvent and aspirin must be the solute. Okay, let's take a look now on the right how we can solve this problem. So again, what they're asking us to do is to calculate the vapor pressure lowering, which is delta P. We just derived that expression earlier that delta P is equal to mole fraction of solute times the vapor pressure of the pure solvent. So we're going to have to calculate mole fraction. That means calculating number of moles. We have number of moles of aspirin. I found the molar mass here that was given the question. And so this is the number of moles of aspirin. The number of moles of methanol could also be calculated. And that's the number. And then so all you need to do is calculate delta P, which is take the mole fraction of solute. Mole fraction of solute, since aspirin is solute, number of moles of aspirin divided by the total times 101 torr. That's the vapor pressure of the pure solvent. And so we end up getting 0.713 torr. So it's a very small decrease in vapor pressure compared to what the solvent. So that tells you that the vapor pressure of the solution is actually only 101 minus 0.7. So it's really still pretty close to 101. So there's not much of decrease. But as we'll see later on when we discuss other colligative properties, we'll find that it actually, even though it's a small decrease, actually affect other properties of the solution, like the boiling point. So the example we just looked at is for a non-volatile solute, right? But remember that you can also have a volatile solute. So in other words, your solute itself could generate some vapor pressure. This typically happens when you have organic liquid. They typically will boil at a low enough temperature that they would generate their own vapor pressure. So if you have both solute and solvent being volatile, then the total vapor pressure is just going to be the sum of the partial pressures generated by the two components, which is the solute and the solvent. So in this case, we just need to expand the expression for Raoult's law to include both solvent and solute. So it looks something like this. The P total is going to be the sum of the partial pressure of the solvent, which can be calculated by taking the mole fraction of the solvent times vapor pressure of the pure solvent, and then the partial pressure of the solute, which we can calculate by taking the mole fraction of the solute times the vapor pressure of the pure solute. So again, we're just adding the two components together, but each component's partial pressure is calculated by Raoult's law. Okay, so an example of the question is shown right here. We have the vapor pressure of pure benzene and pure toluene. They're both organic liquid and they both have their own vapor pressure, right? So 95.1 and 28.4 millimeters of mercury respectively. And then you prepare a solution where the mole fraction of benzene and toluene are both 0.5. So 0.5 each adds up to 1. The questions are, first, what's the partial pressure of benzene and toluene? We can calculate that using equations right here, right? Each one of them would be corresponding to one of those compounds. And then what's the total vapor pressure? We just need to add those two numbers together. And then the last thing is, what's the composition of the vapor equilibrium with the benzene toluene solution? So that question you have to think a little bit about. The idea there is that you have now two components in your liquids, right? You have, let's say, all of these guys. Maybe that's the benzene, and then you also have your toluene in there, okay? And then both of them can form some gas. Same thing here with the benzene, can form some gas. And so the question is, in the vapor phase, what is the relative proportion of the benzene and the toluene? So we're going to have to calculate, in other words, the mole fraction in the vapor phase, okay? So let's go back here to the right side and let's take a look at our problem. So as I said earlier, for part A, all I need to do is use Raoult's law for each one of these. So to calculate the partial pressure of benzene, I just need to take the mole fraction of benzene times the vapor pressure of the pure benzene. I was told the mole fraction is 0.5. This is the value for benzene, so I get 47.55 millimeters of mercury for partial pressure of benzene. I repeat the same process for toluene. I get 14.2 millimeters of mercury. For part B, the total is just the sum of the two partial pressures, which ends up being 61.75 millimeters of mercury. Now, part C is the one where we have to think a little bit. So as I did earlier in the lecture note, drew it again here. So again, illustrating that we have two different particles, one red, one blue, and they both are volatile, so they generate their own gases on top of the liquid. And then so what we're trying to calculate is the proportion of each of those gases in the mixture of gas. So that means we're really trying to calculate the mole fraction of the benzene gas and the mole fraction of the toluene gas. To calculate the mole fraction of the benzene gas, really it's just asking what is the proportion of that pressure that comes from benzene. So it's really taking the partial pressure of benzene divided by the total partial pressure. You might remember this actually from Gen Chem 1. We had used this expression as well when we're talking about Dalton's law in gases to try to figure out the proportion of gases in a mixture of gases. So this is exactly the same idea. So when we take those two numbers, which is the partial pressure of benzene divided by the total, we get 0.77. So in other words, we're saying that in the gas, 77% of that gas is going to be benzene. And then, of course, the toluene would just be 1 minus that number. So that ends up 0.23. Or you can calculate it using the partial pressure over the total pressure expression again.